So this is a heating unit, or it's just a heater, resistive heater, and the question is, what voltage does it run on? Because it's not marked anywhere on this little aluminum package. And that's fairly important because if you apply the wrong voltage to a heater, it might heat up to more than a temperature it was designed for and burn out the insulation and just destroy the unit. So we want to get kind of a ballpark, how much power was this designed for, and I'm going to do that using a voltmeter, and actually not a voltmeter, it's the ohm meter, the resistance setting, and we're going to use the resistance of the heater to determine how much current would go through a certain voltage and how much power it would dissipate. And then we'll just take into consideration the thickness of the wires and if we think it's a reasonable assumption. So first, let's go ahead and measure the resistance. And there's only two wires. You really can't mess it up. There's no polarity. That is, it'll measure the same resistance whichever way you touch. So it says 0.391, but then up in the corner there's a K, the kilo ohms. So that's really 391 ohms. So I'm going to say that R equals 391 ohms. And now let's make an assumption that we'll say at 120 volts, it's really volts AC, but we can call it, we'll just call it 120 volts. And then the question is how much current will go through the heater, because at a fixed voltage and a known resistance, you can figure out how much current will go through. And that value is going to be the voltage divided by the resistance, which makes sense. The more voltage, the more current, and the more resistance, the less current. So we can punch this into our calculator real quick. 120 volts divided by 391 ohms is 0.307 amps, 307 milliamps. Is that a lot of current? Does that make sense? Well, let's do another calculation to figure out what the power dissipation would be. So power is equal to voltage times current, which is also a simple calculation. That's just 120 volts times the current, what we just calculated, 0.307, and that is 36.8 watts. So now what we could do is, we're basically asking ourselves, do these numbers make sense for how thick these wires are? And sometimes that can be hard to know with only one, we've assumed that the voltage is 120, and I'm thinking 0.307, yeah, I think these wires would definitely be able to carry 0.307 amps. Maybe they could handle a little more. Let's try something else. Let's just assume that what would happen if we powered it off of, say, maybe a common voltage is like 12 volts DC. So what would happen if we powered off at 12 volts? Well, it's kind of convenient to check because it's exactly 1/10 the voltage of 120. So I don't need the calculator for this. I just know that the current will be 0.0307 amps, and the power will now be, it won't be 3.68 watts, since it's voltage times current, and the voltage is less and the current is less. It's actually going to be 1/100th of that, which is 0.368 watts. So now I can look at this and say, wow, this is definitely not a 12 volt device, because if the power dissipation is less than a watt, it will barely heat up. However, 36 watts will definitely get warm. So I would say that this device is probably 120 volts Perhaps you could run it on 220, but it is 39 or 391 ohms. It would be way too high to use with a low voltage. So it's kind of cool to be able to do these calculations, and ultimately you're just kind of ballparking things. The higher voltage you put across the coils or the resistor, the hotter it's going to get. So just plug in common values, and then obviously, like, you don't have to try 72 volts because what systems are designed for 72. Like, it's just a bizarre number. So pick a couple common values and do the calculations, and some of the choices will be apparent that they're not what was intended. Anyway, that's how I would do it. Maybe there's more sophisticated ways of specking out the ratings of a heater, but I'm going to say that this device would be safe to operate at 120 volts AC.